Okay, good afternoon, everyone. So today we're going to cover the next section, which is section 1.6 on logarithms. And then we're going to have a quiz at the end of class. So I guess a couple announcements. We're still 2 days behind in terms of the schedule, so just keep that in mind if you're tracking the syllabus. So today we're going to kind of recap what I said at the end of section 1.5 last time, because I felt like I sort of had to rush there at the end of last lecture. So I want to recover what I was talking about there. And then we're going to talk about section 1.6. Okay, so other than that, you have a homework assignment, which is due tonight. Okay, so the last chance to have office hours before your homework is due is going to be today. I need to push my office hours back by 30 minutes today. So they're going to be from 3:30 to 5 on Microsoft Teams. So you can just connect via Blackboard, get on the link, join the team, and join the call. So that's office hours. Don't forget that homework is due tonight at 11:59 p.m. And I've already posted the next homework. So after today, we'll cover section 1.6. So you can probably do the first few problems on the next homework after today's class. And that one's going to be due, I don't remember when, like 2 weeks from now or something like that. I'll give you the exact date next time. How about that? It's like February 7th or something like that. Anyways, the next homework is longer. So I know that there weren't that many questions for this homework, this first homework. Okay, but as we go forward, there's going to be more questions on the homework just because you have so long to do it. I'm going to add a couple extra problems for each section just so that everyone gets the practice that they need to do well on the exam. So I recommend start early. I'm aiming for about like 4 or 5 questions from each section that we cover. Okay, so for each class that we'll have, that's not too many homework problems, I don't think. So just let me know if you need help with that. And SI sessions are still happening. Okay, Monday 8 to 8:50, Wednesday, Thursday 6 to 6:50 in the Close-Hip building. Close-Hip? I think that's what it's called. All right, any administrative questions? Okay, just a reminder that the quiz today and all of the other quizzes, the format is going to be 2 questions long, and the first question from all the quizzes is going to be chosen from the extra problems, okay? So if you do all of the extra problems at the end of each section in our notes, you'll be well prepared for at least one of the quiz questions. Okay, and by the way, it's perfectly acceptable for you to come into my office hours and ask me about the extra problems and try to solve them with me in order to study for your quiz, okay? So I have no problem going through the extra problems with you. But I'm not going to post the answers to the extra problems other than the ones that I discuss with students during office hours. Will get posted onto the Blackboard under the filled out notes section. Okay, so any other administrative questions before we start on material? Oh, one more thing. I had somebody post on the anonymous survey that they didn't really care for the group work because it takes up a lot of time and didn't seem to get through as much material as we could get through, which I kind of agree with to some extent. It's definitely time consuming to do the group exercises. I don't want to eliminate group work completely, but maybe what I can do is compromise with that student and say, what I'll do is I'll try to make sure that the group work exercises are some of those more difficult exercises or like high cog tasks that you might really kind of need to put your heads together in order to solve. And that should hopefully avoid the situation of people doing group work and just everybody does it on their own and doesn't really have to interact with other people. But the purpose of the group work is really just to make sure that all of the students in the class are actually engaging with the material actively and trying things on their own. So I'm not going to be able to get rid of it completely, but I will try to make it as helpful as possible. Okay? Fair? All right, let's start then. So today, I wanted to quickly go back and rediscuss this thing that I was talking about at the end of class last time, which was how to find the equation of an exponential function given 2 points. So what's on the screen right now basically shows you what to do. Okay, maybe we'll have one more line here. Okay. So this is the very general formula for what we are going to do. Okay, so this works if you know what T1 is, and if you know what T2 is, and if you know what P of T1 and P of T2 are. Okay, so we'll see an example in just a second of how this works. But the way it works is we essentially get 2 equations, okay? So we have P of T1 equals P naught A to the T1, and P of T2 equals P naught A to the power T2. And our goal is to find out what is P naught and what is A. So we have 2 equations with 2 unknowns. So what we want to do is somehow combine these 2 equations in such a way that I eliminate one of the variables. Okay? And the method there is to divide the 2 equations. Because if I divide the 2 equations, since both of them have P naught in them, when I divide the 2 equations, I can cancel the P naught, and I'm left with just A to the T2 minus, or over A to the T1, which of course we can rewrite as A to the T2 minus T1. Okay? And then the left-hand side is just numbers, which I already knew from the start. So I have a number is equal to my variable to some power, which I know. So all I have to do is take that power's root, C2 minus T1, on both sides to find A. Then once I have A, I can just back substitute into one of my original equations. Okay, so I know what's on the screen here. It looks like a bunch of gobbledygook. But let's see what it actually looks like when we try one. Okay, so add page. Okay, that didn't go where I wanted it. I want it to go up there. There we go. Okay, so we're going to do this example, which I did with some other students. So the example is find the exponential equation which passes through the points 3, 4, and 564. I think that's the one, yeah. Okay. So, the way I like to start all of these problems, and by the way, it won't always be formulated like this, okay? It won't always say find the exponential equation which passes through these 2 points. They might actually kind of hide this information in terms of a word problem. So, Brendan, the word problem you were asking about earlier, they say, okay, in 2011 there's 4 goldfinches, right? So you have to figure out what does 2011 mean in terms of t, and then what are these points going to be like? So you'd put, if 2011 is time t equals 0, then your point would be 0, 4, because there's 4 goldfinches at time t equals 0. Okay, so sometimes this information will be kind of encoded in a word problem, but I just want to show you how you generally do this process. Okay, so we know that our equation P of t, okay, has the form P naught A to the t. Okay, how do I know that? I know that because it says it's an exponential equation, okay? Okay, exponential equation. All right, so I know this is the general form I'm going to use. And now all I'm going to do is I'm going to plug in these 2 points into this equation to get 2 new equations, okay? I don't know what P naught and A are, but I do know that when T is equal to 3, which remember T is always the independent variable, okay? T is the independent variable. So these 3 and 5 are T values, okay? My T1 and my T2, right? So if I plug in T1, I know that if I plug in P naught times A to the power 3, I get 4, okay? Because this is the height of the function. The height of the function is given by plugging in the independent variable into the function, right? So I get P naught times A to the 3 equals 4. And my other equation, I do the same thing. P naught times A to the power 5 equals 64. Okay, so these are my two equations from the previous page, right? Only now I've got specific numbers. Okay, so remember I have two equations with two unknowns, but since both of the unknowns are actually being multiplied by one another, I can't say subtract these two equations from each other to get rid of one of the variables. What I have to do is actually divide these equations by one another. So it doesn't matter which one you pick, but I'm going to pick this one to be the numerator and the other one to be the denominator. Okay? The reason is I like to have the bigger power of A in the numerator. It just makes things a little easier. So let's do it. P naught times A to the power 5 divided by, now I'm going to divide the left sides of these equations. P naught A to the power 3. If I divide the left sides, I should also divide the right side. So I get 64 divided by 16. No, what am I doing? 64 divided by 4. I'm getting way ahead of myself here. Okay, 64 divided by 4. And now the magic happens. I can cancel P naught. Okay, and I can simplify the left-hand side. Okay, if I do A to the 5 divided by A to the 3, I can rewrite that as A to the 5 minus 3. Okay, which is just A squared. And that's equal to 64 divided by 4, which is 16. Okay, so now I can take the square root on both sides, and I get A is equal to 4. Okay, so this is the trick. We take both equations, and we divide them by one another to cancel P naught. And then we can find out what A is. So now I know what A is. I can update my equation from before, okay? I'm going to take this guy, and I'm going to update my previous equation, okay? Instead of P naught times A to the T, I'm going to write P naught times 4 to the T. Okay, and now my goal is to find out what is P naught. Okay, well, all I'm going to do is actually plug in 4 for A in one of these two equations to find out what is P naught, okay? So I'll do the first one, say. Okay, I'm going to plug in 4. So I know that P naught times 4 to the third power is equal to 4. So now my goal is to find out what is P naught. Well, all I have to do is divide both sides by 4 cubed. So I get 4 to the 1 divided by 4 to the third power, which is 1 over 4 squared, which is 1 over 16. So now I can go ahead and combine all of these to get my final P of T, which is 1/16 times 4 to the T. Okay? So this is the process. On the previous page, I just wrote it in its most general form, but this is an example of how it plays out when you have specific numbers. Okay, so once again, the method is set up your equations, divide one of them by the other to cancel P naught, then use some form of root to get your A. Back substitute A into one of your original equations to find P naught. Are there any questions about this example? Yeah.
How do you know to equate the T to
You mean how do I know to even write down p naught a to the 3 equals 4? Is that your question?
No, not that. Because you set the two functions equal to each other, even though the a's have different powers.
Well, the way I see it, I've written down two different equations. The first equation is p naught a cubed equals 4, right? And then a completely separate equation is p naught a to the 5 equals 64. But these are not the same equation. They're different equations, and each of them comes from their respective point. Okay, so this one comes from there, and the other one comes from here. Is that what you're asking about?
Yeah, but if they're different equations, then how can you equal them, or how can you divide them?
Oh, okay, so how can we divide two equations like that? Well, here's what it basically says is, okay, if I take these two numbers and I combine them in this way, then I get 4, okay? The other one says if I take these two numbers and combine them in this way, then I get 64. Well, all I'm saying in the next step is, well, this thing on the left is equal to 4, right? So if I put it in the denominator, it's still equal to 4, right? So the right-hand side denominator is equal to 4. So this number divided by this number, since the top number is equal to 64, I can make the top number on the right-hand side 64. And since this number is equal to 4 and it's in the denominator, I can put a 4 in the denominator. So it's just different ways of representing a number. So when I write p naught a cubed equals 4, what I really mean is that that expression there is actually 4, right? But what I'm trying to do is break it up in such a way that I can figure out what are the component parts. Okay, but this is just a fancy way of writing the number 4. So when I write this here, it's just a fancy way of writing the number 4. So all this equation really says is that 64 divided by 4 equals 64 divided by 4. Is that clear? Yeah, great question. Any other questions on this example? Yeah?
What does P naught stand for?
P naught stands for your original quantity. So you can think of the 0 as being O for original, or you can think of the 0 as being 0 for time t equals 0. It's what you get when you plug in t equals 0. And I'll show you what I mean. Our equation, right, is P of t equals P naught a to the t. What happens if we plug in 0? P of 0 equals P naught times a to the power 0. Now a is a number. Any number to the power 0 is equal to what? 1. So this is P naught times a to the 1, or sorry, just 1, which is just P naught. So this is the significance of P naught. It's what P is equal to when t is 0. Yeah, good question. Any more questions on this? Okay, I strongly recommend that you practice this. I think I put a couple homework questions on this that you can practice with, but I'll almost certainly put something like this on the first exam. Okay, so just want you guys to be aware of that. All right, I think I'm going to move on from exponents now and talk about something which is related to exponents, which is logarithms. Okay, so we're going to move on to section 1.6 now. Okay, for the sake of time, we're going to skip the warm-up here. And then today, there's not really much on our agenda that we can really sink our teeth into, so we're going to do most of this just kind of together as a class. I don't think we're going to break out into groups for these small tasks. And then we'll have the quiz at the end of class. Okay, so what is the logarithm? Well, in mathematics, we have all sorts of ways of doing things to numbers, manipulating numbers in certain ways, and we have also other ways of undoing those processes, right? So for example, if I add a number, okay, I can undo that process by subtracting a number, right? Or if I multiply by a number, I can undo that process by dividing by a number, right? By that same number. So one thing that we want to also be able to do is undoing things like taking that number as the power in a new function, okay? And this is where logarithms come in. And logarithms help us, okay, to solve equations like, okay, why can't I move the screen? I cry every time this happens. I don't understand. Come on. Why? Okay, we're getting there. Okay, this helps us to solve equations like this, okay? 3 to the x equals 29, where the unknown quantity, okay, is in the exponent, okay? Logarithms are going to help us to get them out of the exponent. Okay, so that's what we're going to do. So let's write down what logarithms actually are, okay? The natural log, okay, I'll say log instead of logarithms most of the time, of x, which we write as ln x, is the power of e needed to get x. Okay? The power of e needed to get x. In other words, okay, ln of x is a number, c, such that, okay, this little sign here means if and only if, okay, ln of x is equal to c if and only if e to the c is equal to x. Okay. So, what does this really mean? I guess what it means is if I say ln of x, okay, what I'm talking about here is the number c such that if I do e to the c, I get x. Okay? Ultimately, logarithms are one of the things that my students at least in the past have struggled with the most. Okay, so don't feel bad if you're confused by this initially. We're going to do a ton of practice to see what this really means, okay? But the key here is if I plug in a number into the natural log function, then out comes another number, and it's the number such that if I do e to the c, I get my original input back, okay? And this is just a fancy way of setting up what is ultimately an inverse to the function e to the x. So important fact, f of x equals e to the x, and g of x equals ln of x are inverses. Okay, now what does an inverse do? An inverse really just means that f of g of x is the same as g of f of x is just x. Okay, so what does this mean informally? It means, okay, I have a function g. It does something to x. Then I put whatever I get into f, and I receive back my original input. Okay, which is telling us that whatever f is doing, it's undoing what g originally did. Okay, so if we think about our functions in terms of these conveyor belt systems, okay, here's what it means. It means we have two functions, okay, g and f, okay, and we put in a number x, and then that number gets transformed into a different function, okay, or a different number. And then we put that number into the f box, and out pops our original number back again. Okay? So in some sense, the G box is doing something which the F box then immediately undoes. All right? That's the idea behind inverse functions. Any questions so far? All right, let's go through this together. It's going to be extremely useful anytime that you have an equation involving natural logs if you think about it in terms of this equivalence, okay? So anytime that I have an equation like this, I typically write out the other corresponding equation just to make sure that I've got my wires all straightened out and going where they need to go, okay? All right, so let's complete these statements here together as a class. All right, so all we need to do is apply this definition to some of these problems here, okay? So basically, they're giving us 1/2 of the exponential, or of this equivalence, and we're supposed to tell them what the other half should say. Okay, well, if in this case we've got y equals ln of 100, okay, y equals ln of 100, then what's going to be true about this equation? Well, the 100 from the input goes over to the right-hand side, and y is going to be the number such that what is true? What should go in my blank here? Well, I'm hearing some different things here. One thing I heard was ln. Okay, in this case, ln of 100 is equal to y, but it's not necessarily true that ln of y would be equal to 100, but it's also kind of hard to see here. This is actually a power of y, so we need to write a number here, and then this will be the power of that number which we take. Okay, so this is a power. It's a little hard to see. So what should go in this box here? Yeah, e. Okay, we put e in here. All right, if y is equal to ln 100, then e to the y equals 100. Okay, e to the y equals 100. All right, let's do another one. So next one, we got ln of 5.5 is the power of blank that gives blank. How do we feel about this one? ln of 5.5 is the power of blank. Well, every time we're doing a log, we need to be thinking about, well, this number here is what we get when we do e to that number, okay? So I think in this case, it's the power of e that gives 5.5, okay? So we don't always write y equals this thing. This thing on its own represents a number, right? And it represents the number such that if I plug it into the function e to the x, okay, then I get this number back. Okay? All right, let's do one in the reverse direction. Okay, so now we've got ln of blank is the power of blank that gives 500. Okay, ln of blank is the power of blank that gives 500. Well, what are we always doing powers of with ln? We're always doing powers of e. So I think we can safely put e there. And then what should go in our box? Yeah, 500. Great. Okay, we're getting this. We're getting the hang of this pretty quick. Okay. And this one is pretty much a straight copy and paste from what's up here, right? They just switched up the letters on us. So e to the m equals n. Okay, in our case, n is like the c, right? So, or sorry, in our case, n is like the x. So I'm gonna put the n where the x goes on the other thing, right? And then the m was the power. So the power from my previous thing became the right-hand side in my new equation. So that's why I'm going to put m on this side here. Okay, so e to the m equals n. This implies that ln of n is equal to m. Okay? Any questions so far? Did you have one, Gianna? No? Okay. All right. So let's see how this actually works when we have real numbers. Okay, so in this case, ln of 5 equals 1.609. Okay, I want to rewrite this using exponents. So I should have e to the something equals something. How should it go? Do we want e to the 5 equals 1.609? No, what did I mess up there? I put the exponent where the argument should go, okay? If you want to check this and you have a calculator, just plug it in. It won't be right. So you can try it out. 1.609, this is going to be equal to 5, right? Okay, the way you can read it out loud is log base argument equals power. Okay, so if you rewrite, okay, the base here is e because we're using the natural log. The argument, okay, is 5 here. Argument meaning what's inside the parentheses. And then we've got power, which is on the right-hand side, so it becomes the power. Okay, sometimes people like that kind of verbal way of writing it down. All right, next one is an easy one. ln of 1 equals 0. Well, the only way we could put this together would be e to the 0 equals 1, right? Because e to the 1 would just be e, and we know that e is not 0, so the other way just wouldn't be right? If we did e to the 1 equals 0, this isn't true, because e is like 2.7 something. E is roughly 2.714 dot dot dot. Okay, so I think this is getting a little repetitive. We can move on to the other direction, okay? Oftentimes we want to use logs to rewrite an exponential equation, right? Okay, and you can think about it in the following way. All we do is reverse this process, okay? We always come back to this equivalence. ln of x equals c if and only if e to the c equals x. So the c needs to go where the c goes. The x needs to go where the x goes. All right? So in this case, we've got x equals 15. I'm sorry, we got c equals 15. And we've got x equals 32. Or 3269017.373, not 32. Okay, so then we do ln of 3269017.373 is equal to 15. Okay, so that's how we switch back the other way. All right, last example, e to the t equals h. This is getting really repetitive now. All we do is, in this case, I guess, you can think about it in terms of the power. C is t, and x is h. From our correspondence earlier on, we know that this should be ln of h equals t, right? Okay, so any questions about logarithms so far? All we've really practiced so far is rewriting a logarithmic equation as an exponential equation and rewriting an exponential equation as a logarithmic equation. All right, if there's no questions, then we'll move on. We're going to talk really quickly about the properties of logarithms, and then we're going to get to the application. So how much time do I got? Okay, I got enough time if I move quickly. All right, there's some properties of logarithms which are really important, and really, in particular, there's one which is super important. But we're going to talk through a couple first. I'm not going to prove these logarithm properties, I'm just going to tell you that they're true. So ln of a times b is going to be equal to ln of a plus ln of b. We also have ln of a divided by b is going to be equal to ln of a minus ln of b. Okay, so these first two properties basically say the same thing. It says if we multiply things, then we can split it up as an addition. Okay, if you want to see the proof of why this is true, talk to me after class. But it's useful to be able to take things like this sometimes and rewrite them as ln of a plus ln of b, or sometimes it's useful to take two logs and write them as one log. It just depends on what we're trying to do. But there will be questions on the homework, surely, that ask you to split them up or combine them back together. And these are the rules which we use to do that. Okay, the third rule is the most important rule of logs. It's why logs were invented, and it's the best thing ever. It says that ln of a to the power p is equal to p times ln of a. Okay, why is that useful? That's super useful because, like I said, later on we're going to have questions like 6 to the t equals 3. And we want to know, what is t? Well, we're going to use this logarithm to apply it to both sides, and that's going to help us to get the t out of the exponent, because otherwise there's no sensible way for us to solve for that t value there. Okay, so that's where we're headed with this. So if you remember one property of logarithms, please let it be number 3. Okay, it's the most useful thing ever. We can take the p from the exponent inside and write it as a product on the outside. Okay, and the last two properties, 4/5, are ln of e to the x is equal to x, and e to the power ln of x is also equal to x. You see that? Okay, so these two are really just what we wrote down earlier on in terms of e to the x and ln x being inverses, right? If I plug one into the other, this is the situation where I'm plugging in e to the x for x in the equation ln x. And what does it give me? It gives me back my x. Likewise, if I do e to the ln of x, it gives me back x. So this equation is like I'm doing nothing, really. I start with x, I do something to it, then I immediately undo that, and I get back my original quantity. Okay, so I guess one more thing here, this is kind of an afterthought, is ln of 1 is equal to 0 because e to the 0 equals 1, right? Likewise, ln of e is equal to 1 because e to the 1 equals e. Okay, any questions about these properties here? All right, if not, let's see some examples of how this works. So these examples are probably the easiest ones you'll ever do. Okay, we're just going to apply our rules here to do problem number 4. We're supposed to evaluate e to the ln of 17. Well, which rule is going to be pertinent for evaluating e to the ln of 17? 3? I would use 3 if I saw something to a power. Well, I have e to a power. I guess I could take ln of both sides, but that might be a little excessive. I think there's one that applies more directly. Yeah, 5 applies directly, right? It says e to the ln x is x. Well, I've got e to the ln 17, so what do I get? 17. Okay, e to the ln, these processes undo one another. Okay, how about the next one? Again, we're going to use property 4, right? Ln of e to the 3. What do I get? 3. Very good. Okay, this one's got a little bit more substance. What should I do here? Any of my rules that I can apply? 2. ln of a divided by b is the same as ln of a minus ln of b. Yep, that one works. So let's do it. Ln of, we get, our a in this case is 1, right? So we get ln of 1 minus ln of square root e. Okay, and by rule number 6, we know ln of 1 is 0. So this is just ln of square root of e. Can we simplify this any further? Yes. How can I simplify it further? Yeah. A square root can be written as an exponent. Okay? Square roots can be written as a 1/2 power. This is the same as ln of e to the power 1/2. And now I can apply rule number 4, right? Ln of e to the 1/2 is just going to be 1/2. Okay, so that one's a little trickier.
Would you keep the negative?
Oh yeah, thanks. Yeah, I missed that. So this is negative ln of e, this is negative ln of e to the 1/2, and this is negative 1/2. Yeah, you could also just rewrite this initially, right, as ln of e to the negative 1/2, right? Because dividing by a square root is the same as a negative 1/2 power. So you can use rules, what was it, rules 2 and 4 combined, or you can just use rule number 4 if you know how to rewrite a square root like that from the start. Any questions on these 3 problems? Okay, fairly simple stuff. All right, so now, okay, this is an example of the types of problems that you'll run into on like a homework or a quiz, right? We just rewrite using the rules, okay? So in this case, they want us to take a log that's combined and uncombine it. And then in the next circumstance, they say we want to take logs which are uncombined and recombine them. Okay, so on this first example here, how can we uncombine this one? What's a good first step? Someone help me out. Yeah, subtraction is what I hear. So really we're referring to the fact that there's a division happening inside. So I know I can use rule number 2, which says that ln of something being divided by something else is the same as those 2 logs being subtracted. So I first get ln of 3x squared minus ln of yz, and I can further uncombine some of these. The first one, for example, I can use rule number 1. Since it's a product between 3 and x squared, I can do this is the same as ln 3 plus ln of x squared. Minus, I'm going to do the same thing to the second one, right? I've got a product here. I can use rule number 1. We get ln of y plus ln of z. Okay, one thing we need to be careful about is if we have a subtraction here, the subtraction needs to get distributed onto both of the terms. Okay, so that's why I put these little brackets here, is to remember that I got to distribute that minus sign. Okay, one last rule I can use. What is it?
Third rule.
The third rule, the most important rule ever, can be applied to the middle term, right? Or the second term. ln x squared can be rewritten as 2 times ln of x minus ln of y minus ln of z. All right, and now we're all the way uncombined, right? We've got logarithms which just have a single argument, right? Okay, so that's one direction. Any questions on that one? Okay, it all comes back to these rules, okay? So write these on a note card and put them under your pillow at night and absorb them into your brain and through your dreams, okay? Because those are the ones that you need to remember. When you're doing your homework, for example, it might be really useful to have these rules on a piece of paper next to you. Okay, so rewrite each of the following as a single logarithm. Now we want to go the other way. Well, how can I rewrite the sum of two logs? By multiplying them inside, right? We get ln 3x minus 2 ln y. How do I treat this second term? Yeah, I can use the most important rule of all of logs and bring that 2 inside as a power. I got ln of 3x minus ln of y to the 2. Did anybody do that step a little differently than me? There's one other way you can do it. Yeah?
If you bring up the ln 3x into the numerator and treat it as a fraction.
Yes, that's going to be our next step, right? But what I meant was that on this step, we have two choices. We can bring the 2 inside, or we can think of this as being ln of 3x plus negative 2 times ln y, and put in a negative 2 for a power, if we want. It's just two different ways of getting to the same spot. All right, so now this becomes, of course, we combine using rule number 2, I think, for division. Like Brendan was saying, we just divide. Okay, we happy with that one? All right. Gotta make sure I don't run out of time here. So let's actually see why this logarithm stuff is useful. So I promised that it would be useful for solving equations where our unknown quantity, okay, where our unknown quantity is in the exponent. Okay, so say we have some equation like 3 to the power t is equal to 10. And our goal is find t. Okay, goal is find t. Well, we're stuck in a bit of a pickle here because up until we learned about logarithms, all we can do is kind of just try out different numbers. But one thing that you'll notice, right, is if we plug in 2 here, what are we going to get? If we plug in 2 for t, you'll get 9. So that's not quite where we want it to be. But also if we plug in t equals 3, we get 3 cubed, right, which would be 27. So our number here is somewhere between 2 and 3. So it's not a perfect square of 3 or a perfect cube of 3 or anything like that. So we got to be a little bit more creative. And the creative way that we solve equations like this is apply log on both sides. Okay, that's how we do this, okay? And we'll see how this helps us. If we have two numbers which are equal to one another, if we plug both of those numbers into the ln function, then those numbers will also be equal, okay, because it's a function. And now, does anybody see what I can do here? Yeah, I can use the most important rule of all of logs and move the t down to the front. Okay, this can be rewritten as t times ln of 3 is equal to ln of 10. And now, ln of 3 and ln of 10 are just numbers, okay? That's one thing that I want to be emphatically clear about, is ln of 3 and ln of 10 are just numbers, okay? So I would solve this equation the same way as I would solve an equation like t times 2 equals 7, right? How would I solve that equation? I'd divide by 2 on both sides, right? So as long as I have t times a number equals another number, the way I solve this is just by dividing by that number, okay? And I get t is equal to ln of 10 divided by ln of 3. Okay, and these are numbers. You can plug them in on your calculator. ln of 10 is the power such that if I do e to that power, I get 10. ln of 3 is the power such that if I do e to that power, I get 3. Okay? They're just numbers. Any questions about this example? Okay. So let's see if I can find a good example down here. Why don't we do, I don't know, C looks kind of complicated. Why don't we try C? Okay, so one thing I do want to be a little bit careful about with this technique is when do I use it? Okay? So what I want to do is first reduce the equation to the form, number to f of x equals other number. Okay, this is what I'd really like to reduce it to before I apply my rule. Okay, and you'll see why. If I just go ahead and try to apply ln to both sides here like this, I'll get ln of 500 equals ln of 200 times 1.03 to the x. Okay? And on this right-hand side, it would not be correct to then write that this is equal to x times ln of 200 times 1.03. Can anyone tell me why this would not be a correct line of reasoning? Adria?
Because the x only applies to the 1.03.
Exactly. The power of x is only applied to the 1.03. Our rule with logarithms said that ln of a to the p equals p times ln of a. Okay? This is not the same thing. This does not mean the same thing as ln of ab to the p equals p times ln of ab. Okay? These are not the same. So I shouldn't use this technique. What I should do rather is eliminate this 200 first by dividing both sides. Okay, and I get 5 halves equals 1.03 to the x. So now I have my equation in terms of a number to something with x is equal to some other number. Okay? So I got to be careful about, I can only apply the rules under the specific circumstances under which they're written. Okay, so now I can go ahead and use my trick. ln of 5 halves equals ln of 1.03 to the x. And now since I have a single number here, and it's being raised to a power, I can bring that power out. Okay, and now, again, I have a number equals x times a number. I want to get x by itself. It's being multiplied by a number right now, so the process is to then divide by that number. Divide by that number. So we get x equals ln of 2.5 over ln of 1.03. Questions about this example? Yeah, Bailey.
If we just know that the first form's going to end up in the last, do we have to show our work of getting there, or can we just put it straight in that form? Because if you know that it's just going to flop around.
You mean like, what would I say if you just wrote this and nothing else?
Yeah.
I would say that I'd like to see you do a little bit more work here. Like, I'd like to see this step written out at least.
Okay.
But yeah, you don't necessarily have to write all of this stuff, but show as much work as you feel like it should show that, yeah. If you wrote this, I'd be like, okay, you could have easily copied that off of someone else's paper. But if you write a little bit more, I can at least see your reasoning.
Like the first two steps, like dividing and then getting the 5 halves, 2.5, will it always go into that form of the ln 2.5 over ln 1.03?
Yeah, okay, yeah. You're technically, so your question, I think, is if you have a equals 1.03, okay, no. If you have a equals b to the x, your question is it true that then x is going to be equal to ln of a divided by ln of b?
Yes.
Yes, this is true. But I wouldn't recommend memorizing it and just using it like that. Okay. Any other questions? Okay, if not, I'm going to move on to one more topic before we close for today, which is converting between exponential forms. Okay, the two common exponential forms are P of t equals P naught a to the t. We've already seen this one. And the second form is P of t equals P naught e to the kt. Okay, and this is a really common way of writing an exponential form. Okay? For the first one, if a is larger than 1, we get growth. A less than 1, we get decay. Sorry. If we do the second one, okay, what we want to think about here is, well, when is e to the k going to be a number which is bigger than 1? It's going to be a number which is bigger than 1 if k is larger than 0. Then we get growth. And if k is less than 0, then we get decay. Okay. So the important way to relate them just notice that if we set them equal to each other, we get a equals e to the k after some cancellation. Okay, we divide on both sides by p naught, we take the tth root, and we get a equals e to the k, which we know also tells us via our logarithmic correspondence that ln of a is equal to k. Okay, take the natural log on both sides. The k comes, actually the k is just directly becomes k because e to the x and ln are inverses, right? Okay, so this is going to be how we switch back and forth between these exponential forms. Oh, thanks. But we're going to close there for today, and we're going to start our quiz. So please clear your desks, except for a pencil. And if you're wearing a hat, please remove your hat. If you're wearing an Apple Watch or other smart watch device or smart device anywhere on your body, then please remove it as well. Please keep it face down on your desk until everyone has a quiz, then we'll start together. All right, everyone have a quiz? You can start.